What's more fun than Truss calculations on the board? Truss calculations on a post-it note. So, a quick thing here. We're going to first calculate our reaction forces. We do that with moments. We choose our pin A as our point of rotation for our first moment. So we have two things going on here. We have 100 pounds being applied at 2 feet, and we have B at 5 feet. Here's maybe a little bit different than this if you are in first period. So but you can just change your numbers. So to figure this out, we're going to say the moment at the 100-pound force is going to be equal to the moment of reaction B at 5 feet. So basically what we get to is force of 100 times the distance to the 100 has to equal the force at B times the distance to B. We know the force of the 100 is 100. We know the distance to the 100 is 2. We're not sure what reaction force B is, but we know the distance is 5. So 100 times 2 is 200. That has to equal 5 times reaction force B. From that we can solve for reaction force B with a little bit of algebra, and we can see that 40 pounds is the amount of force that the ground pushes back up at point B. Since point B has a reaction force upward of 40 pounds, that tells us that the A reaction force must have 60 pounds to balance out this 100. So reaction force at A is 60 pounds. So that the sum of the two forces up at A and B respectively balance out the 100 pounds down. Once we know those, we can zoom into joint A. Joint A is at 80 degrees. Member AC is at 80 degrees from the AB axis. So I'm going to set this just below here and redraw joint A. So joint A has a couple things acting on it. It has reaction force A acting. It also has member AC acting. And it has member AB acting. For us, all that we're really interested in right now is reaction force A is 60 pounds. And so we know that if this is pushing up with 60 pounds of force, something has to be pushing back down with 60 pounds of force to keep that bridge in equilibrium. As we see, there's nothing perfectly in the y dimension there, so there must be some y component that is not drawn. And that, in fact, is this. We say that this member right here, FC, is pushing down to the left. Down to the left means that it has two components. To the left and down. This down component right here, F, A, C, and the Y, has to equal FA, the upward force, which is 60. So we know F, AC in the Y dimension is also equal to 60 pounds. Looking at this, we know this angle is 80 degrees. So we know this angle is 80 degrees. If we know this angle right here is 80, this makes this side the opposite side. So FAC is the opposite side, and it's equal to 60. Since it's the opposite, our equation is hypotenuse times sine of theta. Hypotenuse is this AC force. So we're doing now 60 equals FAC times sine of 80. When we divide by sine of 80, we're left with the force AC. I'll leave you at that.